if I okay. Now, we have looked at the conversion from transfer function to state space. We have looked at the controller design, and the controller was to use 7.250 times x1 and x2 plus r, something like this, minus sign here. So this is our feedback law. Now, it might be the case that not all x1 and x2 are measurable, or it might be expensive to measure this. So for those circumstances, we have to kind of build a observer or use an observer that gives us the states that we want. Now let me show you something. Let's assume that I have a transfer function 7s plus 6, which is gx itself. This is u, this is y. What I can do with an observer is the following. I can use the state space realization of my choice, and I can use that. So I'm going to build something like this, ax plus bu, and let's have this y equals cx plus du, and a correction term, so something like this. Now, the inputs of this observer are meet the input. We have u here. We have y, we have to measure that too, so that's also an input. And our output would be the states. Now remember that I have basically an integrator. We have this derivative here that gives us this. Therefore, we have a plus, and we need bu, so let's have c times this as an input. And we need the output relation here. So c, and since, let's see, this is u, what I can do is I can use basically this times e. Add it here. This would be then my y bar. Then I'll take the difference of these. So in this case, y is plus, and then this portion is a minus. This would give me a certain error vector. I'm taking an L vector here. That's my correction term, and I have to add it back here with plus. And yeah, basically my output then becomes this internal thing. Because I have this, I can just have x bar. So this is basically the internals of this. You can see we have cx plus du, that gives me the output, and I'm taking the difference of the actual system output and my output, or the observer output, take the difference, feed it back here as a correction term. I can have the input and I generate basically x. And you can do this, or imagine this as a Simulink model that has the actual system as a transfer function, and you're just dragging and dropping a state space model there. And well, here you can see I don't have the actual x values, but I can come up with this feedback L, or the Limburger observer coefficient, such that this x bar is basically tending to x, the actual states of the system. So it's possible to design this, and I've shown you the internals and everything. Once I have done that, the only thing that's left is to then use k times x bar as the control difference. So you can just connect it back into U, and all the system has a observer that generates the x vectors that are necessary to build this safety path law. So, how can we design this Sternberger observer? Well, since this is E, the E derivative here needs to be a stable, autonomous dynamic. If that's happening, then the limit t to infinity will show us that E will tend to infinity, because it's an autonomous system. If it's stable, it will tend to 0. It's a linear system, therefore it will end up in being 0. If you have designed the state feedback controller for the first time, you will see that if we design a certain k here, we don't really get reference strength. Of course, we change the poles of the closed loop system, the behavior of the system, but it doesn't track anything if you design this system here. I can add a u equals kx minus kx plus r, but then there will be a steady state error since it corresponds to a p-type controller. It doesn't have any integral in it. An integrator gives us the power of reference tracking, but this is not the case. Therefore, all of these closed loops, when they don't have really an integrator in them, will tend to 0. So the states will tend to 0. If r is 0, of course. If this is 0, then x will also tend to 0 because it's a stable autonomous system then. And here we have the same. Now, since I need the error dynamics, what I'm going to do is I'm defining x and x bar difference being the error. And if I take the derivative, I can directly see that I have x dot and x bar dot because I know what the model is. The x dot is basically ax plus bu, and here the difference wants me to use the observer. This is basically ax bar plus bu plus L, y minus y bar, but cx plus bu is y, and cx bar minus bu is this is y and this is y bar, so the difference. So I kind of get these equations here, and we can see that bu and bu cancel each other out. Bu and bu cancel each other out. What we're left with is ax minus ax bar, and then plus lcx minus lcx bar, or this is basically x minus x bar is e, so ae minus lc, and x minus x bar, so lce. So therefore we have a minus lce. If this is a stable system, an autonomous system that's stable, then E will tend to 0. If E tends to 0, X bar will tend to X. So the observer will work if A minus LC is a stable matrix. And since it looks like a state feedback controller, since the state feedback controller looks like this, it's kind of the same. And in order to show you that it is the same, since this is the unknown here, but the unknown is here, if you take the transpose, you'll just get the same effect. The transpose will show us that A transpose minus C transpose L transpose, so E times that on the left, E transpose derivative, something like this, would be our equation. Now, the correspondence here is that if you have A, instead of A, you can use A transpose. Instead of B, you can use C transpose. Instead of K, you will get L transpose. So the Ackermann formula can therefore be used like this. 0, 1, and then the controllability matrix, let me write it down, B, and then AB, and then A squared B, etc. The inverse of that PD, A. So here, instead of B, I'm writing C transpose. Instead of AB, I have A transpose, C transpose, A transpose squared, C transpose, etc. And then PD, A transpose. So that's it. You can use this formula in order to design your observer. But this here is actually something that we know. It is C, A times C, A squared C, transpose, PDA transpose. And this is basically the observability matrix. Of course, there's also an inverse of this whole thing. This is basically phi O inverse transpose. And if you take the whole transpose, you end up in the Lindbergh observer version of the Ackermann formula, being L equals, they will change order, so you will have PA transpose, and then the observability matrix inverse, and then 0, 1. So 0, 0, 0, 1. So that would be then that. And you can show that since this is a linear combination, the transpose of the transpose is really not that important. You can just use PDA instead of double transposing it. Times phi O inverse times 0, 0, 0, 1. Of course, it's up to you. You can use whichever you want. You might stick with the Ackermann formula for state feedback and then just use A transpose and C transpose instead of A and B. Once you have L, don't forget to take the transpose and you're good to go. Now, this formula helps us in designing an observer, and since the poles of the state feedback were at minus 3.5 plus minus I, or J, I can estimate the settling time of this would roughly be equal to, I guess, no, it's zeta omega, so 3.5, I guess. Yeah, the real part, 4 divided by 3.5. It is around 1 point something seconds of settling time, not really that important. So, if my control action has a certain settling time, my observer should be way faster than that. Maybe 10 times, maybe 20 times, it depends on you. And the reason for that is that following your x bar to x takes time, and this would be the settling time of your observer. So TS observer. And this should be small enough in order to meet this requirement here. Since if it's almost the same settling time, like 1 second, your control action will be done in 1 second, and your actual states will be provided to you in 1 second. Therefore, you would basically feedback false data, and therefore your system will not work as expected. So you should be fast enough, and if you want to design an observer, maybe 10 of this would be a good estimate. Therefore, if you are designing a Lindbergh observer, what I would choose for PDS, let me use this part here. If I would choose PDS, it would look like S plus 0.35, S plus 35 squared maybe, because there's no reason to choose any other thing. X1 and X2 would have these poles, so it would take roughly 4 divided by 35 seconds, so roughly 0.1 seconds to estimate or to get the states of the actual system. So this would then be PDS of the system for the Lindbergh observer. The PDS for the state feedback controller is not the same. It should not be the same. You should choose faster poles for your observer than the state feedback. So that's basically it. You can check out the response of the Lindbergh observer and all the numerical details from the PDF. And this is basically question 9, and this also concludes our today's discussion.